Thank you. Everyone having a good time? Yeah, it's a cool conference, isn't it? Great sort of space. Technology is a fun thing, so I'm using someone else's laptop, and we'll see how that goes here. So, what am I here to talk about? So, we're at a technology conference, and I want to talk about code. We mostly like code, don't we? We all find fun with it, but I'm going to talk about a different type of code. Codes of behavior and how then it interacts with other codes that we deal with. Now, the certain codes are important. For me, one of my important codes is having good coffee. So I like to have good coffee wherever I go. Sometimes it's difficult to get. Particularly in hotels, they seem to send people on courses to make the world's worst coffee. It must take training in some places. So you have to do unusual things. Like this, for example. So how can you make coffee in a hotel when you're kind of desperate? Bring your own pot. Most places have an iron. Use your trainers that you go running with. This sort of thing can kind of work. And the thing is, like, we do interesting things whenever we develop software, and we get proud of some of what we do, and we sort of think, yeah, this is actually really cool, and I'm doing something really neat and interesting. But the problem is, this is not what we really want to be doing all of the time. So much software I see is kind of like this. People are proud of it, that they've achieved something, rather than doing something in a reasonably sensible way. Because whenever we work together and we do really interesting things as teams, as Jessica pointed out yesterday in her amazing keynote, we can do really interesting things, not just the cool individual things. Like, we're able to do things like this. Take pictures of black holes, which is building on the work of generations that have gone by, and we end up coming up with really new and interesting ways to see the world and do different things. So we start to learn a lot as we go forward. Here, I want to talk about the protocols, and the protocols that we use as people. Because when we use protocols, we can interact on a level that we achieve great things, much more beyond what an individual can do. And I'm going to kind of leave this question kind of hanging, and we'll come back to it at the end. Like, are protocols the most significant discovery in human history? You probably think, protocols are boring. I also find that when people come into it, well, it's not just encoding messages. Wait till we finish and see if you think the same at the end. So what is a protocol? Because I think we often misunderstand these things. So let's go right back to the dictionary and look at what is a protocol. Well, one way is described as a code. And this is where the origin of writing code comes from. That's an idea. But it's about etiquette and precedence. The precedence is actually really important in this. So what is the order in which we do something? Now, sometimes we do things out of order. That causes problems, particularly in distributed and concurrent systems. And then how should we treat things? How do we behave correctly given the right sort of views? That's the sort of more general term on it. In computing, we often hear this, where we're talking about the set of conventions governing the treatment and formatting of data. So often in this industry, we just think about the formatting, and that's actually missing a lot of the really important points in here. The treatment is much more important, and that's about the etiquette and precedence. And we'll go into this in a good bit more detail. But before we jump into technology, let's go way back and look at some of what we've learned as sort of scientists, as people, and how we have come forward from this. But the origins of protocol actually start in evolutionary biology. Well, all probably have heard of Charles Darwin. His work on Origin of the Species is one of probably the best pieces known in science. But he did a lot of other really interesting work. And part of that was how people behaved. He studied behavior quite a lot before that, and particularly things like facial expressions. He discovered that people can apply facial expressions almost anywhere around the world, and they're universally understood. We actually communicate very well with expressions. In fact, if you take people who have not even had introduction to language, and this has happened, unfortunately, in some parts of the world where people had an upbringing, they were feral, but as a result, we discovered that they still can communicate in certain ways. We can express certain ideas. Like, we probably understand joy quite well, but things like disgust are actually much more fundamental, and they build on a lot of what we need to survive. And so disgust is actually one of the most commonly used expressions in the world that's understood right across languages, right across cultures, and it's really important to our survival. I'll kind of come back to that a little bit. So as we move forward from evolutionary biology, we then sort of get into manners and we get into etiquette itself. We probably have all heard of manners and heard of etiquette. The origin of etiquette goes back to France around the time of Louis XIV. And at Versailles, the concept of etiquette was first sort of popularized. And etiquette literally means little card or little note. And what used to happen was, how do you behave in the Palace of Versailles? Well, there's all these little notes everywhere telling you how you should behave, like keep off the grass was actually one of the genuine notes of that time. And so these little notes helped people behave, helped them understand what they should do. And then we can do things as a society if we follow these rules. Now, manners can be broken down into three categories. At the basic level, we have hygiene manners. And this is all about the prevention of disease. This is where things like the disgust comes in. It's like we don't deal with things that are dirty. Kids even kind of know this, is you sort of back off from certain things because it's disgusting. That means that you hopefully won't propagate disease. You won't spread things. And so this is a kind of fundamental thing that everybody has hardwired into them. Now, I would kind of argue we should do this much more with technology. So some technology is so disgusting, we need to express exactly what we think of this. Like, I've seen a lot of JavaScript in my life. I've been programming for 30 plus years, and over the years I've seen some things that are pretty nasty, and then some stuff that is just downright disgusting. We should, as individuals, express our disgust much stronger about some technology that we see, and hopefully we'll stop some of the really horrible stuff spreading and sort of try to populate the good stuff going forward. And we sort of express our joy with things that we do like. What other types of manners do we have? Well, the next step up from hygiene is our courtesy manners. And this is all about how the society becomes more important than the individual. By showing courtesy, we are saying and we're demonstrating that we as an individual are not as important as the overall society. Let someone else go first. Let someone else eat first. Sort of self-deprecation becomes an important thing. And without this, we don't function as a large society. And there's quite extreme examples of this. So if it was a case of everything was about the individual, you take even basic societies, you tend to find people fall into different groups. You'll find farmers, you'll find warriors, you'll find scholars, all sorts of different things. But the warriors could very easily take the food from the farmers, but it would be a very short-lived thing. You have to function as a society by showing some basic manners for making it work. The next level up from that are what are known as the norm manners. And we normalize ways of being, behaving, and as a result, we can build trust. And trust is fundamental to trying to do things efficiently, because we can circumvent a lot of process and make things a lot simpler if we have trust in place. So there's kind of really interesting history to quite a bit of this. How advanced can this get? Well, some of our most advanced stuff is in the military. We have rules of engagement, which is basically about how we deal with war. And to society, war is so destructive, we have to define what we believe is acceptable. Because if we don't have a basic understanding of what is acceptable, the consequences are pretty bad. I seen a great keynote a number of years ago by a guy called Mike Jackson, General Mike Jackson, very famous British general from modern history. And he describes warfare really kind of in an interesting way. He says the whole point of war is not to crush your enemy. It's not to beat them. It's to change their mind. You look at these things from, it's like you have a disagreement. How do you change someone's mind? So you've got to look at what are the good conditions to succeed. And success is not the obliteration of everyone. That's really bad for humans as a level. Like, this is actually encoded, and we find it encoded in two bodies of law. Just ad bellum, just ad bello. First is the right to go to war. It's actually really important that you don't just go to war. You have to go through everything as a protocol, and you go to war as a last resort. So you use diplomatic processes, you behave in a certain way, and only if you've exhausted all of the diplomatic process do you actually have the legal right to go to war. If you haven't followed this part of statute, you're technically a murderer rather than a soldier. And so there's kind of interesting history to this. Once war has started, there's still rules around how you're allowed to engage. Like, at simple levels, you've got to treat prisoners fairly, you've got to not indiscriminately kill, but you've also got to be proportionate. So, for example, if you had a ship attacked at sea as one country, and you happen to be the much stronger country, maybe you have got nuclear weapons, it is not acceptable if you have a ship attacked to go and use nuclear weapons on someone else's capital. That would be a war crime. And so it was interesting how this is well developed through history, and there's a lot we can learn from this as we go forward. Now, how does this apply to concurrent and distributed systems? There's kind of a lot to be taken out of some of this and how we go forward. Because what we want to talk about here is, how should components interact? How should components in our systems interact, and how should they behave as they deal with each other? Now, good examples of this, one of the best is the IETF, the Internet Engineering Task Force. It's got some well-documented protocols for how our systems should interact, and we can learn from a lot of this, and some of it's actually quite good fun. Like, on the 1st of April each year, they happen to release a new protocol. Here's a good example from 1998 on how we control coffee pots using a protocol. And so it's kind of fun, but it gives some good examples of how to do stuff. Like, you read this stuff and you learn from it, but also you have a bit of fun along the way. Like, if you dig into this, you'll find out there's an error code 418, which a teapot can return to say, I'm a teapot, I'm not a coffee pot, so you can't control me as a coffee pot. This thing goes further, and there's actually even more informative stuff. This is one of my favorite ones from this. So going back to 1980, probably some people were just children and not even born then, but we had this one, the Holy Wars and the Plea for Peace. If you ever have heard about encoding your protocols, and you heard about Little Indian and Big Indian, what does all of this mean? This is the best description of it. And what's the origin of Little Indian and Big Indian? Well, if you've read Gulliver's Travels, in Gulliver's Travels, there's two parts of the nations that go to war. And they go to war over how you should eat your eggs. Do you eat your egg from the big end or from the little end? And that's where Big Indian and Little Indian comes from. Now, in technology, we apply it as which byte or which bit should be sent first when we're dealing with a message. So do you deal with the big bit first or the little bit first? And that's a Big Indian, Little Indian. It's the same sort of idea. This paper is wonderful. I really recommend people go read it. It's incredibly funny and very informative. And if you want to wonder how we encode numbers in computers, it covers everything that we need to have. Some other gems that are in there is how to have IP datagrams sent over avian carriers, pigeon post. So how to send stuff around the world using pigeons. That's 1990. Some of this stuff gets updated, like we took avian carriers and we added quality of service whenever that became a cool thing in 1999. And more recently, we updated it to cover IPv6. So there's some kind of interesting stuff. So notice, but all of these documents that I've shown, they're all just plain text. There's nothing overly fancy, but they're actually full of some really good content and some really interesting things in there. And there's a lot we can learn from that. So how should we document our protocol? Should it just be basic text? Sometimes yes. Should it be something much more? I like to sort of take a step back for a second. API versus protocol. I find this an interesting debate. We all talk about API design. I think API design is kind of missing the point. It loses so much. Our APIs are very much one-dimensional. We lose a lot of the depth, lots of ways of looking at stuff. Take, for example, a file protocol. If I can open a file, close a file, I can read and write. What if I described my file interaction something like this? So I can do an open, followed by any number of reads or writes, followed by a close. I have now specified precedence as well as what the calls are. I find that when people do this, when they start designing their services, it becomes much more powerful. It's easier to understand, but it's easier to deal with it. And also, it flushes out a lot of ideas in how we think about systems. And so this is just one way that a few people tend to do is they tend to use like a pseudo-regular expression syntax. You could use extended Beckes-Nor form. There's various other ways of doing that. But once we've specified the precedents and what the major actions are, we can go on to document what each of them are after that. It's not a very onerous process. It's actually really simple, but very powerful as a way of dealing with stuff. And we can learn a lot by picking something up that has these sorts of simple documents. It becomes very easy to deal with. The best way to think about this is events. So anything you're interacting with, you interact via events. So something happens, you choose to interact with that event, and then you decide to what you're going to do next, what sort of behavior you're going to apply. So when we start thinking about this, we start thinking pre and post conditions. This will sort of help you with the precedents, what should happen, what are invariants in the system. This is a good way to sort of think about how things should behave. What is okay? What is good conditions to succeed at any given point in time? Start thinking like this. We can start bringing out a lot of what we've learned in other protocols into our systems. But most importantly, think about what can possibly go wrong. I find this is probably one of the biggest weaknesses, one of the biggest immaturities we have in our industry is we don't presume that stuff is going to go wrong. But in concurrent and distributed systems, things go wrong all the time. And it should be something we just treat as normal, and we deal with it, and we do a good, sensible job. Now, if you want to read a great paper, so one thing to take away from this, read this paper if you do nothing else other than see this talk. It's a brilliant piece. And it's talking about how most critical failures in systems are to deal with poor error checking. People don't check errors well enough. There's lots of interesting things. So it talks about how when we analyze real systems, you'll see that some of them fail because of they haven't checked errors, because they've done various different things. But this is analysis of things that had P1 production issues, where the system completely stopped, and what was the most common cases. Like virtually, as people went through this, they started seeing like 75% of all of the cases they seen were P1 could have been caught by a unit test. But my favorite piece from it is, what's wrong? One of my slides has gone missing because I'm using someone else's computer. The next slide was going to say 25% of the errors in this were cases of where we had exception handlers, that there was nothing in the exception handler. They were just ignored errors. In a number of those cases, there was to-dos that were just left in the code base. Please fix this before we go into production. And it was never fixed. 25% of production outage errors were people not actually handling errors that were known, that just weren't dealt with, they just weren't tested. It becomes really important that we kind of do these sorts of things. Let's go for a more interesting example. So that's some background. Let's look at a practical, real-world algorithm and what can we do about it. So let's say I wanted to build a chat system or a whiteboard or some sort of shared interaction tool where we've got this common state, and then that common state needs to become visible to all of the clients that are using that. All of the users, they need to be able to see that common view. Well, typically a good way to do that is to multicast out the state from the central service so that everyone can see what that is and have their local view. Now, there's some interesting problems with scaling that. So if the data is all sent out and the data can go missing, so if it gets lost, what can we do about it? Well, one of the things we can do is we can acknowledge all data that's been sent out, and that way we can detect loss and we can retransmit. But that has got a bit of a problem. It doesn't scale. If you're acknowledging everything you send, you start increasing the amount of work with the numbers of clients connecting to something. So we've got a scalability problem. We could use multicast UDP, and we can send out, that's going to get lost as well. But how about rather than sending out an acknowledgement for data, because actually data loss is less common than it being successful, we'll do a negative acknowledgement. So we'll say, I haven't got the data, and we'll resend that data. That ends up in another interesting problem where we can get a thing called NAC implosion. So just like we've got the issue with ACKs, NACs have got a dark side to them too. And the problem here is that most loss tends to be correlated. So, for example, if my server is sending out the data, and it goes to send out the data, and there's a buffer overflow in the router or the switch or whatever is sending it out, there's not enough space, it drops the packet. That means all of the clients lose that packet, they don't get it. Then they'll all start requesting the packet again. And as they all request the packet, that's a lot of requests coming in for the packet. The server will then send back the packet multiple times. Now, the reason it dropped the packet is probably because it was overloaded. So now we'll get an implosion. And this becomes a really difficult problem to deal with. Now, this is where people typically naively design systems going back some time. And then someone came along and had an idea how to do it better. That person was Sally Floyd, and she wrote this paper, along with a few other people. And she came up with this really nice algorithm where the idea was that you send out the data, and then whenever you realize you've got loss, you don't just request the data straight away. So what happens is all of the clients who realize there's loss, first thing they do when they realize is set a random timer. And that random timer is going to be for a very short period of time, and it's usually determined by roughly how long the round trip is. And what happens is all the timers will go off randomly in that period, and you get a normal distribution. And what will happen is some will go before others, and some will go later than others. So the first ones to go will send back the negative acknowledgement. They will get the data retransmitted. When the other ones go off later, they check if the data has been retransmitted, and if it has been retransmitted, they don't send their negative acknowledgement. That way they've coordinated, but with no central control. It's actually a beautiful little algorithm. No point of central control, adding in some randomness, and coordinating based by everyone following the same rules. They're all following the same protocol. Now, Sally Floyd, along with Van Jacobson, did a lot of great work, particularly in the 1980s and 1990s, that effectively saved the internet. We were suffering from congestion collapse. They contributed in all sorts of areas and did some pretty amazing work. What I find fascinating about Sally is that, yes, she has a master's in computer science. She has a PhD in computer science. Her first degree was in sociology. She thought differently about the problem. Thinking about how it was a society, there's no central control. It actually worked really well. So we get this beautifully scaling algorithm that was very different to most of the other approaches, where we tend to find that a lot of the algorithms in this time all thought command and control and central control. It's very fragile and also doesn't scale very well. Some other people came later and thought, do you know what? That sort of normal distribution we had of data, that's got some issues as well, because it all tends to clump around the middle, so we could probably do better than that. What if we exponentially distributed those timers and skewed it all to the later levels, but made sure enough were happening early, just through the distribution, that we could get the data sent and deal even better with NAC implosion, and probably find out even sooner and cut the latency down? That's what was the result of this paper. Another beautiful piece. But again, no central control. It's about rules to how things play together, and as a result, we deal with really quite nice systems. And it all works out very well. That's a couple of examples. Where should we focus if we're going to deal with protocols on the whole? Like, there's many different points to them. There's lots to consider. Like, we look at layering, versioning. Do we batch? Do we do sync, async? Do we trust these other systems? Is privacy important? Like, all of these things are really interesting. It's a vast subject in its own right. So I want to pick on some of the points and sort of like highlight the importance of some of it. But first of all, kind of ask a question. Who cares about waste? Do we just care? We're just going to burn this planet down and we don't really care? Like, our data centers now are using more energy than the airline industry. We're part of this problem. I know it's one of the biggest parts of the problem. I get to measure lots of real-world systems. I do performance analysis. And by far the biggest problem I see is how we encode our data. We stick stuff in text rather than using binary codecs. By putting stuff in text, we waste vast amounts of CPU cycles and vast amounts of energy. When we look at the formatting side, binary is so much better. It's a much more efficient way of dealing with this. It's easier to parse. It's easier to deal with. But you keep hearing people going, but it's human readable. No, it's not. The thing is, we have good tools that allow us to read text-based data. We have editors. If we have better tooling that lets us read binary data, it becomes a lot better. And actually, if anybody says they can read ASCII, yeah, I know a few people who can read ASCII fairly well. I really don't know many people who can read UTF-8 for anything significant. So to say text is readable, sorry, it got to call BS on that one. It's the tools are there. So we need the better tools, and we can do some quite cool things with that. And if you do, then you get to do pretty things with ASCII art. This is like one of mine where I'm describing protocols, and this is the sort of typical way you'll find things in the IETF, and we just draw things with ASCII, and we can do cool stuff. So this is describing a message being sent in a particular type of system. But then we can parse this and we deal with it much, much more efficiently. And when I say much more efficiently, I'm talking multiple orders of magnitude differences. So stuff like some messages that can be done on CPUs in a few tens of nanoseconds, instead we turn them into JSON and XML and everything, and it becomes hugely inefficient. I'll stop ranting about this and kind of move on. Let's talk about versioning instead. This is something that I found that I understood but didn't really appreciate for a long time in my career, and now I'm starting to really appreciate how important this is and what we can get out of versioning of things. So at the highest level, version our protocols. What conversation are we having? Are we having a later conversation that allows us to have new words and new ways of dealing with stuff? Different ways of becoming more efficient? It's definitely getting more interesting as we're out there. So we need the versioning at that level. We need versioning on the messages themselves. So we can have extra fields in them. One of the things we start to learn when you work in any sort of protocols and distributed systems is you can always add, but you can never take away. Taking away is something that is just breaking in how it works. So the default needs to be is offer the absolute minimum and then add as required. Don't put stuff in because you just think it's going to be useful. Put it in because it's actually required at any given point in time, because we can't take it away, especially if it's an issue. The bit that I find that I'm appreciating more and more every day is the actual versioning of state. It's something we haven't really considered so much. And when you start seeing problems in different protocols and different systems, often it's a case of state being not what we expect. So one example is at a protocol level. Say, for example, I'm doing a consensus system, and I'm going to try and elect a new leader. If I'm voting for something, I want the vote for this election to apply to this election, not a vote from a previous election to apply in this election. So you've got to put a version on what is the election at that given point in time. And good examples of this is things like the RAF protocol and some of the stuff on ViewStamp replication, where this all becomes much easier to understand because everything is versioned. It becomes much more reasonable. And even better if it's versioned at all monotonic. Much, much easier to reason about in this space. But it's more subtle. So distributed systems and protocols have now sort of grasped the fact that things have to be versioned at that level. What about concurrent algorithms? I've done some work in queues, and particularly dealing with multi-producer, multi-consumer queues, which was one of the more complex. And you get a lot of what are known as ABA problems, where you see a version of a state, it goes to another version and then goes back to the same, what looks like the same state again. So the value is the same, but the version's different. It's a different instance in time. And that can cause all sorts of interesting problems. So how can we deal with it? So like one particular queue I had where I had it working, it was working in production in a number of places really well, and then occasionally it had errors. I managed to track down what the problem was, and it was one of these ABA problems. And then started looking around for solutions to this, and I found this website called 1024course.net by Dmitry Yukov, and he has got a really beautiful algorithm, by far the most beautiful algorithm I've seen for multi-producer, multi-consumer queues, and the genius in it is he gives a version number to every state, and that way it just really simplifies. Sometimes you look at algorithms, particularly concurrent algorithms, are really complex. When you look at something, you go, yep, that's obviously right. It kind of just stands out there. And that's one of the things he did is he added the sequence number of the change. So every single change to the system has a new sequence number, and you can then reason about it really well. So applying the versioning even at the state level can really help and makes things a lot more easy to read. Sync versus async, another interesting problem. How does this play out, particularly from a performance perspective? So if I'm going to have a synchronous interaction with the system, I send a message, I get a response. Send a message, get a response. Message, response. You see how time is going out. So to do things, it takes a period of time, and you have to wait for the response. Let's increase the latency. So things take longer to happen. We start dealing with this. Oh, I can't get my 3 requests done. I don't have enough time anymore. We start having these kind of interesting problems that stand out here. And then what's happening when I'm waiting? Well, what typically has to happen is your thread has to be context switched out. You have to wait for the response, then be context switched in. You're using the thread or the state, or maybe you're assigning futures or something to it. It's all a bit of a mess and really inefficient, and getting worse all of the time, particularly with all of our vulnerabilities that are appearing in our CPUs. Context switches are going to get more expensive, not cheaper. It's something that's not going to go away. Well, what if it's asynchronous? So I send a request. I send another one. I send another one. Then I can start getting the responses. And so now I can complete the work in a much smaller period of time. What if I increase the latency? I'm not out of time. It gets much better. It actually scales much better when you've got more requests. If you've only got 1 request, it doesn't really matter. But once you've got 2 or more, this starts to really matter. Well, what's happening in between? Well, you could be doing other useful work. Like, anybody here cook? When you go in the kitchen, you don't put something on and you wait for it to complete and don't do something else. Meals would be really boring if you just did one thing at a time. Well, put the vegetables on, go cook the meat, do something else, and then you get them all done together. There's a lot more can be achieved in the same period of time and much more effective. But we tend to break a lot of what we've learned in other disciplines when we do computing. We can be much more efficient by doing things concurrently, but we need means of managing this and dealing with it. But your protocols need to think like this. But again, it comes up, but, synchronous is so much easier. This is a bit like the sort of text is so much easier. You keep seeing this all of the time. Well, what we have to do is learn to manage state via feedback. This becomes the important thing that we've got to do, is like understanding what is the state we're managing, and we'll deal with that via the appropriate feedback. And this goes right back. Claude Shannon talked about this in original information theory, and yet we're still not building on some of this history. We seem to just keep relearning and recreating everything over and over. Like, go back and read some of Claude Shannon's work. It's from the 1940s. He's already described most of what we should be doing here. But more importantly is think about, this is the real world, and we've got events, and things are distributed in space and time, and we have to acknowledge that, and we have to deal with it. And if we do, things get a lot easier. Now, how do we sort of transition? Well, I keep finding that, well, if you're going to design a system, build it asynchronous. And if you have to, wrap the asynchronous API with the synchronous API to keep all the crybabies happy for a while, until you wean them off it, so just kind of get them used to it. Don't go straight to building a synchronous API. You lock people in forever. It's a terrible idea. It doesn't really work, and go back. Build things from primitives that can go the right direction. Like, some examples in the real world, like, we've learned painfully that RPC is a terrible idea, yet we still see it keep getting reinvented, retried. It's like, let's try again. The next generation has another go at it until they run into the wall and have all the same problems. Like, we built HTTP on top of RPC. HTTP is designed to fetch documents, yet we use it for loads of other things. It's really inappropriate. And then we applied it on top of TCP, which wasn't designed for either. TCP was designed for long-running connections and have a protocol for transfer of files and things, but not the little short things that we typically do. And we also got it all the wrong way around in how we deal with it. So what are we doing to try to fix some of this? So TCP evolved, and we've got TCP fast open to try and get around the 3-way handshake to start stuff. Now if you use a Google service and you've got a Chrome browser, you're communicating with Quick now, which is a UDP-based protocol, not with TCP. So we're trying to fix this under the hood. Like HTTP has gone from 1.1 through Speedy now to HTTP 2, which is trying to be much more asynchronous, trying to not use task-based protocols as we've sort of learned and gone forward. We've also learned that we made mistakes in HTTP 2. And now we've got HTTP 3 because we didn't sort of think about the what can go wrong question. And the what can go wrong is when you're putting everything down the same connection, if that goes wrong, you don't get any of the page. We need to be able to have sort of progressive rendering of a page. And so HTTP 3 is going to address some of that. Like we made loads of mistakes in security, especially with TLS. Now TLS 1.3 is getting a lot better and more performant in how it works. So kind of loads of interesting protocols out there. Like, go read the TLS 1.3 spec. It's actually one of the better ones I think we've done so far. And particularly, this is a kind of interesting one with the come together. So we improve things a lot for performance, but then we realized that we've got this 0 round-trip time to start up a connection with TLS 1.3, but it's vulnerable to replay attacks. Not if you version everything and everything becomes idempotent, then you deal with it. So we've got to build on the layers of doing these things right. If we do it all with versions, it's all idempotent, things get a lot better. If you don't sort of build on those things, you have problems. Batching is really fascinating to how we apply at this level. And without async, we can't batch. This is one of the things I really don't like about synchronous APIs is it just makes batching and inefficiency become a really difficult thing. Think about it as the etiquette of a request. So imagine you go around to a friend's for dinner. And as you arrive, the friend says, do you know what? I need some milk to finish dinner. Could you please go to the shops and get me some milk? So you go to the shop, get some milk, you bring it back again. Now, you come back, and your friend goes, do you know what? I actually need more milk. Could you go back to the shop again and get me some more milk? And so you go off, and you go get more milk, and you come back again. And you get back and say, do you know what? I actually need another pint of milk, and I'd like some cheese as well. And so you send them off. All of a sudden, this friend is not someone you're going to deal with very often. We have hardwired in behaviors and how we treat people. You think about how we interact with the machine. We just don't care. Now, it doesn't have feelings, but we're overriding a lot of how we think about problems. And as a result, we get different ways of thinking. In fact, when we want to be unpleasant as human beings, we deliberately dehumanize others so we can do things that we want to do. We're practicing some of the bad behaviors when we're dealing with computers quite often. Like, think about as we get to 1 gigabit Ethernet, how are we going to get the efficiencies to call and make enough system calls into this? It's a serious problem because we can only do so many per second. It means we can't get the packet rates up. We need to break away from those synchronous APIs. By becoming asynchronous, we can get around that. And there's a wealth of new APIs that are starting to improve and go this sort of way. We can do much better. Once we start thinking about this, we can naturally batch. We start dealing with our natural behaviors. We got to think more about this and show some sympathy for our machines. A bit like how we show sympathy for other humans and how we should be doing this. I'm kind of hoping that by me being a bit nicer to the computers by the time they eventually take over and we become their pets, they'll be a bit nicer to some of us and not to others who've been a bit unpleasant to them. Like a good example is ORMs and SQL. We're making databases do what they're not designed for. It's almost like you've got a friend who's not so tall, and you say, please get me the things from the high cupboard over and over again. It's not a very nice thing to do. We ask databases to pull out all these silly little things when they're really good at joins and doing other stuff. We just don't think about how we interact. There's a lot we can get if we think about it. And then we've got things like, I call the snake oil protocols. Two-phase commit. AXA is a really good example of this. And part of the problem here is we've got corporations telling you we're going to take away all of your problems and we're going to make the world all right. Well, it's just BS. That's all it is. Because you have some responsibilities in this. Things will go wrong. If you read the specs, you start to see. Like another great paper, Jim Gray and Leslie Lamport from 2004, talking about the issues in this. Like, I love this quote. Two-phase commit is not fault tolerant because it uses a single coordinator. The failure of this can cause the whole thing to block. It's just so important to think about it. We don't get absolved from these things. We have to think about it. If anybody tells you their messaging system is guaranteed delivery, I'd call BS on them as well on that. It's just the key. There is no such thing. There is certain responsibilities we have, and that's part of our protocol for how we interact. And if we start thinking about what's the feedback, what's the recovery, we can deal with all of this. We can deal with it and be a lot less fragile. And we build it up in layers. By building it up in layers, we trust what's underneath, we build on the knowledge of what's gone before, and we get better. And once you know your responsibilities, take them seriously, then we can move on. So I want to wrap up quickly as I'm running out of time. Are protocols the most significant thing that we've discovered in human history? What's this protocol? Anybody know? Yeah, scientific method here. Probably one of our greatest understandings, sort of originally Francis Bacon, popularized by many scientists after that, led us to great things like this. Like, by using this method, we can discover the structure of DNA. Like, how cool is this? Like, we can encode 2.2 petabytes per cubic centimeter of this stuff, or a gram. It's just really impressive. But it's all about our protocols, we apply them, how we interact, how we learn. And if we study and practice them more, we can achieve a lot. So think about this on your next project. Do you go and install your favorite frameworks, tools, technologies, whatever? Or do you think about what are the protocols first? What are you trying to achieve? What are the protocols you should apply? Which is more important than this? And think about it from another level. Code of conduct, I think, is one of the most effective ways we've applied protocols as humans. And this has appeared through religions, through everything. It's like, think about how you interact with others. Think about the systems, think about that. Our inner ability to do things quite well, it's how we think about stuff. And if we nurture that, we think about it better, we can often achieve great things. We don't if we just try to dehumanize and don't think about the interactions and trying to do it well. And on that, I'll thank you very much.
Thank you. Thank you very much, Martin. So we still have a little bit time to ask some questions. So if you have questions, put them in the Word document or raise your hand. So I'll give you some time to think about that. Maybe a good question to start off with is, it was very nice to remind us of the use of decoding and encoding. Mm-hmm. For those who are not familiar with this topic, but from your experience, you know, if you need to say, okay, how much more faster is it actually over using text, so that people have an idea on performance gains or efficient?
Let's go to the extremes and show how big it is. So one of the fastest protocol encoders that I know as a codec is SPE. I happen to be involved in the project, so take that with the appropriate disclaimers around it. But we can deal with market data messages in finance and encode or decode those in sort of sub 20 nanoseconds. If you were to take the same thing and do it in Google Protocol buffers, it will take 1,000 nanoseconds. If you were to do it in XML or JSON, you're looking at around about 10 to tens of thousands of nanoseconds, so around about to sort of tens of microseconds. So you're looking at sort of 3 to 4 orders of magnitude difference between dealing with this. That's a lot of CPU cycles. If you actually measure real-world systems, you'll see that the business logic is almost a rounding error. Quite often, it's less than a few percent, and the rest of the time is spent on our whole stacks of technologies that we build up for no good use. And it doesn't really help. And this is part of what's contributing to us having data centers just taking vast amounts of energy.
Okay. Any questions from the audience? This is the time to raise your hand. Well, I'll check on the application or on the document. Anyone? Yeah, Jessica?
I've run out of time. I did want to do them a bit slower than that. So, which ones where do you want me to start or stop? So what I'm talking about here is like scientific method is a protocol. We follow the steps of the protocol. We follow it in order. So think about what is the fundamental question we want to ask. Create a hypothesis that we can then think about how we test. Then we create a prediction for the task that we expect. We perform the test or the experiment, We analyze the results. One of the greatest things we have to learn about stuff. And think of it, all it is encoding basically what we do as children. We play, and we actually build up things in the same way. We should do this much more as adults. So sometimes we stop the things that we do as a natural way of thinking. Like, it took us to things like the discovery of DNA, which I talked about. The theory here was, is it a helix? If it is a helix, it will show up in X-ray diffraction as this, and this was the work of Rosalind Franklin that was happening at King's College, and we got that image. So this was the big step forward. So Wick and Crick and Watson sort of talked about some of this, but it was actually the photograph that proved the theory. But my thing is, like, why are we not studying these more? Protocols are so interesting. It's not just about encoding the data. It's fundamentally how we interact at any level of scale. And if we study them and we apply that study, we can achieve much better things. And to particularly think about this on your next project, because how often you turn up on a project and you just install your favorite technology before you even think about the problem you're trying to solve. And think about those cases of like 25% of errors in production systems that were P1 were unhandled errors. Why is that not baked into your fundamental protocol when things go wrong? Like, if you look at TCP, as soon as TCP gets something wrong, it says a reset and goes back to a particular state in the protocol, which it can handle and go forward from there. You often don't see this in people's system designs. The code of conduct thing is about the golden rule. You see this appear in many, many things. So in religion, sort of in Christianity, you'll hear it said as like, do unto others as you'd like them to do unto you. But it's fundamentally about how should we interact. We should interact with some empathy, with some decency, trying to do the right sorts of things. And I see if our systems do that as well. Think about blame-based cultures. It doesn't create good systems. Melvin Conway talked about how any system takes on the shape of the communication organizational structure that built it. If you've got a pure communication within your organization building something, you will get a poor system because the protocols manifest. It's the same sorts of things. So I would like to make the argument that if we actually want to become much better at what we do in our discipline, one of the areas we should work on becoming better at ourselves is in how we communicate. And what are the patterns of interaction with how we communicate, dealing with the failure cases, dealing with helping out, dealing things in the right way, showing disgust at the appropriate time whenever we see things that aren't right, showing joy whenever we see things that are done well. That way we can get much better at it. So I think we're out of time.
Yes, I think I have one last question before the lunch. So, referring to Jessica's opening keynote, so where she spoke about art, and that actually we didn't have a name for art for many, maybe even thousands of years before people actually decided to call it an art. Would you say the same logic applies to this whole world of protocol development, right? Shouldn't we put it in a separate discipline maybe to stimulate the development of protocols?
It's a good question. I'm not sure I know the answer to it. I think it's key that whenever we want to do things at any scale, we need those interaction protocols. And I think one of the failures we have in industry is we think about the individual too much. And actually there's such limit what the individual can do, and that causes us to create protocols that are fundamentally flawed, like two-phase commit and a single transaction coordinator. Like, it's the structures we apply. We've done it in our management structures. We've done it in how we work. Those examples that Jessica gave were really excellent around how you've got multidisciplinary groups of people sharing with overlapping ideas, overlapping skills, but actually covering a much larger area. And how they interact is what causes the greatness to happen, not the individuals.
Okay. So thanks very much. And we break off for lunch now. So give a warm applause to Martin.
Thank you.